We previously derived this transfer function for the common source amplifier at high frequency. And after analyzing the circuit using the small signal models at high frequency that include the MOSFET capacitors, we solved the circuit equations, and we got this kind of scary formula for the transfer function. But then, after looking carefully at this function, it's really just a function of this, which we can write in this form. In the numerator, I have a degree 1 polynomial. I only have s to the power 1. So this is of the form 1 plus s over omega z. There's 1, 0. And I can tell directly, immediately, what is the value of the 0. It's minus gm over cgd. The denominator looks complicated, but it's of the form 1 plus b1 times s plus b2 times s squared. So it's a second degree polynomial. And the values of b1 and b2 are, we can get them from the expression, and they depend on the resistors and the capacitors and gm. But it's just a second order polynomial. Now I can factorize this and write it in the form 1 plus s over omega p1 into 1 plus s over omega p2. And if I have numerical values, then I can find the values of omega p1 and omega p2. And once I have this transfer function in this form, it becomes quite easy to find the bandwidth, to find the value of the 3 dB frequency, especially if there is a dominant pole. If omega p1 is much less than omega p2, then omega p1 would be dominant, and it would be the value of the 3 dB frequency. And it has to be, of course, less than the absolute value of the 0. But this 0, we can directly judge that it's at a very high frequency. The reason is that gm, or 1 over gm, is a relatively small resistance. Gm is a transconductance, so 1 over gm has units of resistance. So 1 over gm times cgd would be a small resistance times cgd, and 1 over that would be a very high frequency compared to omega p1 and omega p2. So that's typical in these circuits. If omega p1, the smaller pole, is not dominant, then we know we can use the other formula with the square root, or we can even solve this exactly. It's just a quadratic equation. So it's fine. I mean, nothing really very complicated here, except that the expression is too long. If omega p1 is dominant, let me try to get an approximation for that. I can multiply the two factors and say that if omega p1 is dominant, then 1 over omega p2 would be negligible compared to 1 over omega p1. So if omega p1 is much less than omega p2, 1 over omega p1 would be much larger than 1 over omega p2. So 1 over omega p2 becomes much smaller, negligible compared to 1 over omega p1. Of course, this is an approximation, and omega p1 should be very dominant for this to provide a good approximation, an accurate value for the 3 dB frequency. But if this is the case, and I can just drop the 1 over omega p2 term because omega p1 is very dominant, then the value of b1 B1 times S would be 1 over omega P1 times S. And therefore, omega P1 is 1 over B1. So this in the equation, this factor that multiplies S, if I take 1 over that, this quantity here, if I take 1 over this quantity, then this would be a good estimate for the value of omega 3 dB, assuming that there is a dominant pole. And if this is the case, I can also estimate omega P2, and I can estimate it from this, because the factor that multiplies S squared is B2, and it's also equal to 1 over omega P1, omega P2, and I have an estimate for omega P1, then I can estimate also omega P2. These are good estimates if this is very dominant, when omega P1 is not just dominant, but very dominant. So not a factor of 4 less than omega P2, but maybe a factor of 10 or 50 or something like that. So that's it. This is the conclusion. We know that the low frequency gain is minus GMR prime L, and that's not surprising, because if we do the analysis at low frequency, we get this gain exactly, minus GMR prime L. If I had no capacitors, I would get minus GMR prime L. And I see it here in the transfer function. So that's a confirmation. The zero frequency and absolute value at GM over CGD is very high. And to answer the question, what is the 3 dB frequency? Well, if one of the pole frequencies is very dominant, then this would be a good estimate. If not, as we said, we can go back to this and solve the quadratic equation exactly and get omega P1 and omega P2. So this is what we can do with this transfer function. Now, let's go back and evaluate. I mean, this is not as simple as like a low pass STC with like an RC, one resistor, one capacitor. This is more complicated. So let's investigate the source of the complexity. Why is this harder than just a low pass STC? Let's look at the equations that we solved and see where this complexity comes from. These are the equations, and this is the circuit. And if you look carefully at the circuit here, at the input, this side, this is a nice RC circuit here with R prime sig and CGS. On this side, this is also a nice RC circuit because a current source, this in parallel with the resistor becomes like a voltage source in series with a resistor. That's the Norton Thevenin. And then you have the capacitor. So that's really another nice RC circuit. What is complicating things is this guy here, CGD. CGD, imagine the circuit without a CGD, and then you will have two nice simple RC circuits. And we know how to analyze these low pass STC simple RC circuits. But because there is the CGD, I cannot do that. And I have to write all the equations and solve them and get scary formulas like this one. So is there a way to kind of get rid of CGD? The answer is yes. And there is a theorem in circuits called Miller's theorem that would allow us to do that. So what is the Miller theorem? This is an illustration of Miller's theorem. If I have a circuit with an impedance between two nodes, node 1 and node 2, such that the voltage at node 2 is some given multiple of the voltage at node 1, then I can transform the circuit into another one, which is equivalent to the first one, but now with two impedances, Z1 and Z2. but Z1 is from node 1 to ground. Z2 is from node 2 to ground. And the conditions in the circuit would remain exactly the same if Z1 is Z over 1 minus K, and Z2 is Z over 1 minus 1 over K. It's quite easy to show that the currents and the voltage would remain the same if Z1 and Z2 are given by these equations. So that's nice. This is a method to get rid of an element between two nodes if it's complicating my analysis, because it becomes two elements between the nodes and ground. But there is a very important condition here. K should be known beforehand, and V2 should always be equal to K times V1. If V2 is not K times V1, and I know K, and it doesn't change with the conditions of the circuit, I cannot apply Miller's theorem. But if I am given K, I know K, it's constant, doesn't change if I change the conditions in the circuit, then I can apply Miller's theorem and simplify the circuit. Even though I replace one impedance by two, this is an additional impedance here, but the circuit becomes simpler, because if you have elements between nodes and ground, they kind of simplify the analysis, not complicated. If Z is a capacitor, which is the condition we had in the common source amplifier, the impedance was a capacitor CGD, then if you apply this formula, knowing that the impedance of the capacitor is 1 over SC, then the capacitor here becomes two capacitors. This Z1 would correspond to C into 1 minus K, and this Z2 would correspond to a capacitor at node 2, which is C into 1 minus 1 over K. And this is at node 1 to ground. So the capacitor becomes two capacitors. Note that the sum of the two capacitors is not C. We're not splitting the capacitor. C into 1 minus K and C into 1 minus 1 over K, they're very different capacitors. And in many cases, C into 1 minus K would be much larger than C. So this is what we call Miller's theorem. And maybe it's useful because I want to try to get rid of CGD. Can I apply it now to my circuit, to my common source amplifier circuit? Let's do an exercise first, so we're trained on how to apply it, and then we will apply it. Let's take a circuit like this one with a V sig R sig and an impedance between the input. This is the input, and this is the output, and this is an ideal amplifier. An ideal amplifier that gives me a gain of minus 100 no matter what. So K is minus 100. The voltage here at node 2 is always minus 100, the voltage at node 1. All right. So V2 or VO is minus 100, V1 or VI. So this is like an ideal situation, but that's fine. We're just trying to apply Miller's theorem here to practice this its application. And Z is a 1 picofarad capacitor. So this impedance is really just a 1 pico capacitor between the input and the output, or between node 1 and node 2. Of course, I can analyze this circuit without Miller's theorem, but we want to practice Miller's theorem, so let's do that. Since K is minus 100, it's given, it's fixed, I can apply Miller's theorem between this node and this node. I have this minus 100 constant factor, and I have this impedance, which is bridging the two nodes. So I can apply Miller's theorem, and I will get something like this. So this minus 100 triangle, I show it as a voltage controlled voltage source, or I can keep it as a triangle if you want. And Z becomes Z1 and Z2 with C1 equal to 101 picofarad. Where did this come from? This is 1 minus K times C. This is C into 1 minus K. K is minus 100. C is 1 pico. So C1 is therefore 1 into 1 plus 100. C2 is C into 1 minus 1 over K. So this is 1.01 pico. So this capacitor that was here appears in the circuit as two capacitors. One of them is 101 picofarad, and the other is 1.01 picofarad. And the conditions in the circuit are exactly the same as they were before. So if I analyze this circuit, it's like I'm analyzing the circuit on the top. Now, if you look at the circuit, there are two interesting things. The first one is that I have a voltage source and a capacitor in parallel with it. So the voltage here would always be minus 100 VI and is not affected by this Z2. So this is connected across the output, but it does not affect the voltage, because if you have an element connected across in parallel with the voltage source, the voltage will be fixed by the voltage source. So VO is minus 100 VI, not affected by Z2. And for the first part here of the circuit, this is a very simple, nice RC low pass filter, the LPSTC. And we like those. They're now our very good friends. So for the input, I can say that VI over V sig is 1 over 1 plus S C1 R sig. Using the voltage divider formula, it's Z1 over Z1 plus R sig, and Z1 is 1 over SC1. So I get this very nice form. This is of the form 1 over 1 plus S over omega 0, with omega 0 being 1 over this. So omega 0 is 1 over R sig C1. The output is minus 100 VI. So VO over V sig is minus 100 divided by 1 plus S over omega 0. And 1 over omega 0 is equal to R sig C1, which is 1000 nano, 1010. So that's the transfer function. And it's obviously of the form AM over 1 plus S over omega H, or K over 1 plus S over omega 0. So I know that now the value of omega H would be 10 to the 9 over 1010, and the value of FH, if I want it in kilohertz, would be 157.6 kilohertz. So by applying Miller's theorem, basically the solution of this problem became just writing the transfer function of a low-pass STC, of a simple RC low-pass filter. So let's see if we can apply Miller's theorem in the common source amplifier, or the common-emitter amplifier. Maybe we should go back and look at the circuit and see if we can apply it. Let's go to the circuit, and here it is. Okay, let me erase these. And I want to see now if I can apply Miller's theorem here. I want to apply Miller's theorem and get rid of CGD as a capacitor that bridges the input to the output, and transform it into two capacitors, one between the input and ground and one between the output and ground. So the condition to do that, the condition to apply Miller's theorem, is that the voltage here, this is V2, and this is V1. V2 is the output, and V1 is the input in this case. The condition to apply Miller's theorem is that I should know what is K. So what is K in this case? Well, what is K? I am not given K. I don't know K. And if I have K, then I would have the gain. I would have VO or VI. I don't know K. I'm not given K. I have no idea what K is, and I'm not sure it's fixed. It may vary if I remove CGD and replace it with other things. So what does this mean? Maybe we cannot apply Miller's theorem here. And yeah, that's the case. We cannot apply Miller's theorem here. So fine, let's go back. So can't. But of course, there must be a way. And that way is called the Miller's approximation. So I cannot apply Miller's theorem exactly, but I can apply an approximation of Miller's theorem. So there will be an error because of this approximation, but the approximation would allow me to apply Miller. So what's the approximation that we will use? We will use the low frequency mid-band value, or low frequency, just the value of VO over VGS, V2 over V1, that we get if there are no capacitors in the circuit. So we will find K at low frequency and then say that, okay, this is K and it's fixed, it's given, it doesn't vary, and use it and apply Miller's theorem. However, this will not be an exact application of Miller's theorem because K would vary with frequency, and we're assuming that it doesn't. Why it does. But that would be a good approximation and it will simplify things. So that's fine. So we'll go back to the circuit and find K at low frequency and then use it to apply Miller's theorem. So actually, well, we can approximately. So if we use this approximation, that K, which is the voltage here across CGD, divided by the voltage here, is the low frequency value and it doesn't change. So that's the approximation here. Then we can apply Miller and CGD would disappear and become two capacitors. So this is the Miller approximation in common source, common emitter. And here what I had previously as CGD is now two capacitors. CGD into 1 minus K. K is minus GMR prime L. So CGD into 1 minus K becomes CGD into 1 plus GMR prime L. This is between node 1 and ground. Okay, and also I will have another capacitor. I already merged it with CL. So here I had two capacitors, CGD into 1 minus 1 over K. So this here is CGD into 1 minus 1 over K. And I have a CL from before, which was here also in parallel. So I already added them. I did not add at the input. I only added at the output. So this is what we get. So now CGD is gone, thanks to the approximation of Miller's theorem. And I get two capacitors instead of one. All right. Of course, I can add these two. I mean, they're now in parallel. And I'll call this CN, CGS plus CGD into 1 plus GMR prime L. And at the output, I have CGD into 1 plus 1 over GMR prime L plus CL. So did the circuit become simpler? Well, the input circuit is now a low-pass RC circuit. It's a low-pass RC circuit with a resistor R prime sig and a capacitor equal to Cn. The output circuit is also a low-pass RC circuit because I can transform the current source in parallel with R prime L into a voltage source in series with R prime L, and it becomes just like the circuit at the input with a resistor R prime L and a capacitor equal to the C out capacitance, which is CL plus CGD into 1 plus 1 over GM R prime L. So that's good. I now have two LP STC circuits. What's the pole frequency for a simple RC circuit? If you have a simple RC circuit like this, with a resistor and a capacitor, with the input here and the output across the capacitor, then omega 0, the critical frequency for this is simply 1 over RC. That's a well-known result. So now I have two of them, and each has its own omega 0. All right. So what are the omega 0s for these two parts? At the input side, the pole, or the 3 dB frequency for that part only is 1 over R prime sig Cn. At the output, the pole, which would be the 3 dB frequency for that part only, is at 1 over R prime L C out. Usually, but not always, the input circuit determines the high frequency response. So the value of the pole at the input side is much less than that at the output, and it's dominant, and therefore the overall bandwidth is determined by the input circuit. And we can say that omega h is just the pole on the input side. And I know what that is. So no need for complicated circuit analysis. It's almost by inspection. If omega on the input side is not dominant, then we'll have to see how we can find omega h from the two sides. If it is, then we can continue and say that VO over V sig or V prime sig is AM, which is the midband or low frequency gain, divided by 1 plus S over omega h. And omega h is this input circuit pole frequency. And if we want to plot, then we can approximate by just a low pass STC with a 3 dB frequency at omega h or FH. Again, if the input pole is not much smaller than the output pole, if it's not dominant, what do? That's fine. We can use this approximation. So omega h is not omega n. Omega h would be approximately 1 over the square root of 1 over omega n squared plus 1 over omega out squared. So this considers the effect of omega out, but it's also an approximation. And another way to find omega h is maybe find it exactly from the transfer function. How do we do that? Well, what would be the transfer function of the circuit after applying Miller's theorem? It's actually quite easy to find. VI here is VGS. VI over V prime sig is a 1 over 1 plus S over omega n. VO over VI is a minus GM R prime L divided by 1 plus S over omega out. So VO over V prime sig, this is the transfer function, the overall transfer function, is minus GM R prime L over 1 plus S over omega n into 1 plus S over omega out. So it's AM the low frequency gain, minus GMR prime L, over 1 plus S over omega N, the pole on the input circuit, into 1 plus S over omega out, the pole on the of the output circuit. So now this is the transfer function of the whole circuit after applying the Miller's approximation. So this means that this is not the transfer function of the circuit, the exact transfer function of the circuit. This is an approximate transfer function of the circuit. If I want to compare with the exact, we will have to compare with the big formula, the scary one. So this is much simpler, much nicer. And if I want to now find the 3 dB frequency using this one, I can solve a quadratic equation and find the 3 dB frequency from this post-Miller transfer function, the transfer function that we get after applying the Miller's approximation. Now let's move on and talk about discuss this open circuit time constants method, which is an improvement actually over the methods that we have seen, which require that we know the transfer function. So this open circuit time constants method, or simply OCTC, skips this step of finding A of S. And using OCTC, we can determine the 3 dB frequency omega h directly from the circuit. So what we have so far is, if I have a circuit, I would have to find the transfer function, A of S, and then I have many different methods. I can start here, I may be given A of S, and then I have all the methods like dominant pole, approximation using the square root, solving exactly, Miller, all that stuff. Now I have a nice tool set. If I'm given A of S, I'm safe. I know how to find omega h. If I'm given the circuit, well, I have to find A of S first, and then find omega h. OCTC skips this step. You're given the circuit, and you can find omega h directly from the circuit without finding A of S first. So that's an improvement if I don't really care about A of S. I don't want to know all the details about A of S and where are the poles and the zeros. I just need a good estimate, a pretty accurate estimate of omega h. And I have my circuit, I want omega h. Why do I need to find A of S? So OCTC allows me to do that. And this is the approximation that we can use. Omega h is approximately 1 over the sum, this symbol sigma, is the summation of CI RIO. Of course, we will define now all the terms here. So CI is capacitor number I in the circuit. If I have 3 capacitors in the circuit, I will have capacitor number 1, capacitor number 2, capacitor number 3. So I would be 1, and then 2, and then 3. So I have C1, C2, C3 in my circuit. RIO is the resistance seen by capacitor CI with all the other capacitors open circuited and the signal sources set to 0. And then once we find RIO for a certain CI, I multiply RIO and CI. And once I do that for all the capacitors, I add these products. So I get C1 R1O plus C2 R2O plus C3 R3O. So that's the summation. And then I take 1 over that, and that's omega h. So I need to go over the capacitors, find the resistance seen by each capacitor, and then multiply this resistance by the capacitance. and take the summation of all of these products, 1 over the summation is omega h. It's kind of like a magical thing, but we can easily derive it from the actually the transfer function. All right, so what is this resistance seen by a capacitor? The term resistance seen by something, we already, I think we know what it means when we were looking at the resistance seen looking into the drain of a MOSFET and stuff like that. So when we say resistance seen by the capacitor, it's as if the capacitor is measuring the resistance. The capacitor is like a test source, V test, and I want to find the current that is flowing out of this test source. So I replace the capacitor by a test source, V test, and I find I test. And the resistance seen by the capacitor would be this V test over I test. So when I say resistance seen by a capacitor, so this is a capacitor, and it's connected to something. If I want to find the resistance seen by the capacitor, I remove the capacitor and replace it by, instead of the capacitor, I have a test source, Vx or V test, and I measure or I find Ix, and the resistance seen by the capacitor. So what does it see? If the capacitor had an I, it will see Vx over Ix. That's the resistance seen by the capacitor. And I need to consider the conditions when I'm doing this. All the other capacitors should be open circuited. That's good. So remove all the other capacitors in the circuit. Also, set the signal sources to 0. Again, that's good because this will simplify the analysis. So if I have signal sources, I set them to 0. If I have other capacitors, I open circuit them. And then for this particular CI, I find Vx over Ix, and this will be the resistance seen by the CI with the conditions needed to apply OCTC. So here's our circuit. Here's our common source amplifier. Now I want to apply OCTC here. So how many capacitors do I have? CGS, 1, CGD, 2, CL, 3. 3 capacitors. So this is the first capacitor, second capacitor, third capacitor. And now I need to find the resistance seen by each of CGS, CGD, and CL. When the other capacitors are open circuited, the signal source is set to 0. The capacitor is replaced by a test source, and I want to measure Vx over Ix. Great. This looks like fun. Let's start with CGS. If I want to find the resistance seen by CGS, I will call it RGS. I will open circuit the other capacitors. If I open circuit CGD and CL, then this is my CGS. Now I have an open circuit here. So I'm no longer affected with this part of the circuit because CGD is now an open circuit. And then I have R prime sig. And the signal source that's the second condition. I set the signal source to 0. So just like I open circuit here, CGD becomes open, and so is CL. The signal source is set to 0. And now I want to find the resistance seen by CGS. So if CGS were a test source, Vx, what would be the current Ix, and what would be the ratio Vx over Ix? I think this is very easy. It will be just R prime sig. The test source, which is here, Instead of CGS, I have now the test source Vx to find the resistance seen by CGS. Vx over Ix would be R prime sig. There's only R prime sig here. Vx over Ix is R prime sig. So the resistance seen by CGS when I'm doing OCTC is R prime sig. Okay, that was easy. CGD, I want to find RGD. CGD, this is the capacitor that's annoying us. Miller was able to help us get rid of it, but now we're back to finding the resistance seen by CGD. And to find the resistance seen by CGD, I open circuit CGS. So CGS was here, and now it's an open circuit. I no longer see it. I open circuit CL, which is here, so I no longer see it. The source becomes 0. So these are the OCTC conditions. And here's my test source, Vx Ix. And now I want to find Vx over Ix. This is not a simple like inspection type of resistance that I can see. I need to do a circuit analysis. So I have to find the currents and the voltages and then find Vx over Ix. That's fine. We know how to do circuit analysis. This is a circuit with 2 sources and 2 resistors, so not a big deal. VGS is Ix times R prime sig with a minus sign because Ix is flowing to the right. Also, this Ix is the sum of the current in the control source, GM-VGS, plus the current in R prime L. So GM-VGS plus VO over R prime L. And VO by KVL is equal to VGS plus Vx. So I think I have all the equations I need to find the ratio Vx over Ix, which is the resistance seen by CGD under the OCTC conditions. And I get this R prime sig plus R prime L plus GM R prime sig R prime L. Okay, and that's not intuitive, right? I mean, the resistance seen here by this test source is this plus something else plus that's product, like this times this times this. Okay, that's fine. In fact, this is a result that we will use a lot, and we will generalize it into a rule. And we will call this rule the RXY calculation. So if I have a circuit like this, which is similar to the one that we just analyzed, with a resistor Rx on this side and a voltage Vx across Rx, a resistor Ry on this side with a controlled source, controlled current source in parallel with it, equal to Gm times Vx, so Gm Vx, which is here, then the resistance Rxy that I see if my test source is here, this is my test source, the resistance that I would see is this formula, is given by this formula. It's Rx, so the resistor on this side, plus the resistor on this side, plus Rx times Ry times Gm. So Rx plus Ry plus Gm Rx Ry. We call this the RXY formula. And we will make it into a rule because we will need it, we will use it a lot. So this is the resistance seen by a capacitor like CGD in the common source amplifier. R prime sig plus R prime L plus GM R prime sig R prime L. All right, so we're done with CGS and CGD. Now we have CL. We want to find the resistance seen by CL, the third capacitor. And if I open circuit CGD, I open circuit CGS, I set this to 0. These are the OCTC conditions. This actually makes VGS equal to 0, and this becomes 0. And then if I have a test source here at CL, the only thing that it will see is R prime L. So that's the resistance seen by CL, R prime L. That's the resistance seen by CGS, R prime sig, and that's the RXY seen by CGD. And now we have everything we need to apply OCTC, and omega H would be 1 over tau GS plus tau GD plus tau CL. Tau GS is the product, CGS RGS, tau GD is CGD RGD, and tau CL is CL RCL, and RCL is R prime L.